We shall talk about Kubo formula, basically the formalism to calculate conductivity. This particularly we keep in mind about the Hall conductivity, which is the main focus for this course. So, let us see how the Kubo formula is derived, and this is derived within linear response theory. Okay, so this is an example of calculating conductivity within a linear response theory. So, the assumption is such that one has many body system. So, it is not just one particle which we have considered while we considered Schrodinger equation and solved for a single electron, say in presence of a magnetic field. So, there is a presence of many particles, and so we talk about a many particle Hamiltonian. So, this is that many particle Hamiltonian. Now, why I write it with a 0 is that this does not contain the perturbation term that we are going to talk about. However, this can contain interparticle interactions present in the system. Okay, so that is not an embargo here. So, H0 may contain interparticle interaction, and now we are going to talk about the perturbation that is introduced because of an external field. Now, in this particular case that we have talked about, it is the electromagnetic field, rather there is an electric field in the longitudinal direction and there is a perpendicular magnetic field being present. However, it is enough for us to talk about only one kind of field, and that could be, say, just an electric field, but then it can be generalized into both electric and magnetic fields. So, let me write down a general Hamiltonian in presence of an electromagnetic field. We can do a particular case for an electric field later. So, we have said this, that the Hamiltonian actually comprises of P minus QA whole square over 2m, where this A is the vector potential that comes in because of an external field. And one can actually talk about the gauge freedom, because these A, the vector potential, can be uncertain by an amount which is delta lambda, where lambda is a scalar function, and this is perfectly acceptable because even if you add or subtract a gradient of a scalar function, B equal to curl A is still satisfied. So, if we expand this Hamiltonian, and if you want to write it specifically for the electron, then you introduce this Q equal to minus E. So, this is my Hamiltonian. Now, what I am going to do is that I am going to expand this. So, this is a P square over 2m, and then there is a 1 over 2m, and then I have a term, I can write it as E over 2m, and then there is a term which is like P dot A and A dot P. Now, in general, they do not commute, that is why we have to write it separately, but if you choose a particular gauge called as a Coulomb gauge, which we will just see, then these two terms can be combined into one term. And then of course, you have a term which is A square over 2m and E square over 2m into A square, and this term is called as the paramagnetic term, and this is called as a diamagnetic term. Okay. Now, it turns out that we will neglect this diamagnetic term, and in the parlance of perturbation theory, you can say that if B is not strong enough, then A would also be weak. So, a term which is of the order of A square can be neglected. However, we have seen that in our case the magnetic field B is not weak at all, and then we need to take into account terms such as B square or A square. However, it doesn't contribute to the Hall conductivity, even though it contributes to the longitudinal conductivity. However, since the main focus is on Hall conductivity, we will drop the diamagnetic term altogether and only worry about the paramagnetic term. This is of course the unperturbed problem, which is solved in the sense that these unperturbed problem, we know that suppose this and this acts on some wave function psi m will give you a em psi m, and that problem is known. Okay. So, which means that this unperturbed term, which is a part of the many particle Hamiltonian, is known, or at least if you even add interparticle interaction, the assumption is that that problem is completely solved, and we have to only look at the effect of the paramagnetic term. Okay. So, this term can be written as, so we specialize into this term for the moment, which is P dot A plus A dot P. And suppose we act, so this is that the paramagnetic term. So, let me call this as HP, and let this call this as HD, D for the diamagnetic and P for the paramagnetic. So, HP is like this. So, if I want to understand that, how do I do a simplification of this? I consider an arbitrary state psi, and then this will be like E over 2m. Now, your P dot A is minus I h cross del and dotted with A, and plus A into minus I h cross del, and this acts on psi. Okay. So, look at this term. This term actually looks like del and A psi, okay, where A is the vector potential. So, this is like A dot del psi and plus a psi equal to psi del dot A. Okay. So, there are these two terms that are present. Now, you see that this is actually, there are two terms, and these term, if we consider that a gauge where this equal to 0, this is called as a Coulomb gauge, and in this Coulomb gauge it only is left with this term, which is same as this term. Okay. So, with this minus I h cross adjusted there, and so these two terms can be combined, and one can write down just one term, which is, so this paramagnetic term, which now let me call it as delta h or h prime, whatever you want to call it. It is that extra term whose effect needs to be considered, and this is nothing but this is equal to E over I h cross. So, this is a minus I h cross E over m and a dot del. Okay. So, this we want to consider its effects on psi m, okay, which is the unperturbed state. So, we are really doing perturbation theory, but in this case it is slightly different notionally from the perturbation theory that you might have learned in your second course of quantum mechanics, or even in the first course of quantum mechanics. This is done on a system of many particles. Okay. So, once we know this, so our Hamiltonian has a form which is apart from these constants, which we can take into account. So, the constants are like this. This is nothing but, so if you take the minus I h cross, this delta h takes a form equal to, so minus I h cross del. So, this is E A dot P over m, and so the P is the momentum. So, this is P over m is V, and E into V is equal to, so we can write this as there is I think there is a sign that is missed here. So, this there should not be any sign. So, there is a sign that comes here, and that tells you that this V over M, P over M becomes equal to V, and then E into V becomes equal to current density. So, this is actually equal to minus J dot A. Okay. So, we are going to work with this as the perturbation, which is minus J dot A, and this perturbation, the effect of this perturbation to linear order in A is what we actually talk about when we do this. Okay. So, let me write down the perturbation term, and this effect of this would be considered on the conductivity of the problem, and in particular we talk about the Hall conductivity. Okay. It can also be used in order to calculate the longitudinal conductivity, which we are not doing here, but can be done. And also it is important to remember that you need to take into account the A square term, which is nothing but the diamagnetic term here. Okay. So, this is our like our starting point of a perturbation theory in this particular case. Now, in order to proceed further, there are a few simplifications, or even you can call them as tricks. These tricks are being introduced to make life simpler and to achieve the goal in a manner that we wish to, such as there is no need, but of course we take because these fields are DC fields. DC means they are constant fields, either the electric field or the magnetic field. However, we take them to be an alternating field, that is we talk about an AC field, and with which sort of oscillates with a characteristic frequency omega. And as I said, that there is no a problem if we simply talk about just the electric field, even though we know that there is a Hall, there is a magnetic field there which moves the electrons in the transverse direction, and that is how they pile up, the charges pile up at the edges, which gives rise to Hall conductivity. However, we will simply talk about electric field and do a linear response theory only with the electric field. Okay. So, let us consider an electric field of this form. So, this is your E0 and say exponential minus I omega t. As I said, it is a trick, and the trick is introduced at this stage for the reason that we are going to talk about a gauge which requires taking a time derivative, one, and secondly of course keeping in mind that we are really talking about DC fields, we will put omega going to 0. So, as a limiting case. Okay. So, this is a particular kind of harmonic dependence on omega that we have introduced here, and what we do is that, so your E is obtained from minus del A del T. We have taken it is also a minus grad phi, which we can scale it to 0, and the time or this from the Maxwell's equation, the electric field is obtained from the time derivative of the vector potential. So, this is your E of t, and it is precisely for this reason that we have taken it is a function of time, because your A of t it is really like E divided by I omega exponential minus I omega t. Okay. So, this is your A, and if you take a derivative, so so you take a del A del t or a dA dt, that is equivalent. So, we will have a E over I omega, and we will have a minus I omega e to the power minus I omega t. So, this omega will cancel and the I will also cancel, and so on. So, you get this E equal to minus del A del t, that relationship to be valid, and that is why. So, this is the form of the vector potential in terms of the electric field. Okay. So, now we know or rather we have assumed a form for the vector potential, we can put that back into this equation. So, let me now go one step back and sort of start naming these equations. So, let us call this as equation 1, and this perturbation term to be equation 2, and let's call this as equation 3 and so on. So, we have to find this potential, rather this perturbation term, which has a form j dot a, and a is assumed to have a form like this. At the end, after we do all the calculations, we will put omega going to 0 to take the DC limit. Okay. All right. So, let me calculate the current or the expectation value of the current in these perturbed states. So, these states that includes the perturbation. So, we calculate J. So, J is the current density that flows due to this perturbation term that we have. So, we need to calculate this. All right. So, this is the job that we have in hand, and understand that I remind you of 3 pictures that in basic quantum mechanics you might have been exposed to. One is called as the Schrodinger picture, in which you have the wave function that depends upon time, but the operators do not. So, let us call any operator as do not depend upon time. Okay. So, this is the Schrodinger picture, and then we have Heisenberg picture, where it is just the opposite, that is psi does not depend on time. However, the operators depend upon time, just the reverse scenario. And if you remember that we have actually calculated the equation of motion by taking a d dt of O equal to OH, where O is any operator and H is a Hamiltonian. There is IH cross I have to write here, and so this is the Heisenberg equation of motion. A third picture, which is very important for the many particle system. In fact, all the many particle system, the Green's function and all the perturbation theory that we talk about are developed in the interaction picture. And both where both psi and O depend on time. Okay. So, this is in a nutshell, this is the different pictures of quantum mechanics that one deals with. And now, it is very important to realize that when you calculate the expectation value of an operator, which is a physical observable, it will not depend upon which picture you adapt to, rather it will be independent of the picture, and all those results will be same in all the representations. In any case, since I said that in the interaction picture both psi and H are dependent on time, or H means the Hamiltonian, which is an operator that depend upon time. So, we will resort to the interaction picture here, because you saw that the Hamiltonian, or at least the H delta H, which we are interested in, is time dependent through these A, the vector potential. So, we will resort to this picture, and of course, we will have to evolve the wave functions. So, wave functions are definitely time dependent. As the time proceeds or passes by, then the wave function evolves as well. All right. So, any operator, let us say we have been writing it as O, but let us say any operator in this picture, the interaction picture, it evolves as some U inverse A of 0 and U, which is a unitary operation, and U is actually a unitary operator which is written as exponential minus I H naught t over H cross. You can set H cross to be equal to 1, otherwise you will have to carry it all the way. In any case, this is a unitary operation that one can perform on any operator, such as the Hamiltonian, and in this particular fashion, and we'll see the time evolution of the operator. So A is the vector potential. In this particular case, we are not talking about vector potential as an operator. This A is, okay, let me change this then. Let me go ahead with O, because A is already the vector potential, and so on. So this is the O is the an arbitrary operator, and this is your the unitary transformation. So U is an unitary operator. Okay, so this is my operator, and how does the wave function behave? This is also standard. Basically, that comes from this interaction picture. This evolves as some t to t naught, and then psi is t naught. So let's call it as A, and let's call this as B. So this is how in the interaction picture the operator and the wave function evolve. Okay. All right. So we'll have to work in this interaction picture and perform a perturbation theory in order to get the expectation value of an observable. In this particular case, the observable is nothing but the current density. Okay. All right. So this one, the ut of t0 in the interaction picture again is written as minus I by h cross some t0 to t delta of h t prime and a dt prime and so on. Now, it is very important to understand in the interaction picture, this is actually the time evolution operator invokes the perturbation term or the interaction term. Here you can treat both of them to be with interchangeably the what you want to call them. I mean, this same as the interaction term in the language of the many particle systems. Okay. So this is how the unitary operator evolves a system, a state psi of t from an initial state t0 to a final state t, okay, and that involves the interaction term or the delta h that is here. Okay. There is another quantity called as t. This is called as a time ordering operator. Now, if you want to know in details, you can look at these Fetter-Wallachka. There is a book by Fetter-Wallachka, or there is a book by G.D. Mahan, and there are other sources available on the YouTube. Personally, I have a course on these advanced condensed matter physics, which deals with the developing the formalism of the perturbation theory from the scratch. So what it does is the following: it orders the times. You see that there is a t0 to t, and we are writing it as an integral, which means that it goes from t0 to t0 plus delta t, then it goes to t0 plus 2 delta t, and then it goes to t0 plus 3 delta t, and so on till it reaches the t1. So you need to have a mechanism which orders these from the earliest time to the right or left, whichever. I mean, basically to order these times in the sequence that they are occurring. And why is that important? It is important because your delta h at time t1 will not commute with delta h at time t2 in general. Okay. Otherwise, if they commute at all times, then there is no problem. I mean, then the problem is much simpler. And because you have a time dependent problem which explicitly depends on time, and then you need to keep a track the way they are occurring. So this is that time ordering operator that you come across. Okay. And it of course sort of makes sure that the I h cross du dt is equal to some delta h into u, So that is the Schrodinger equation for, or the equivalent of the Schrodinger equation for the operator. So that's the time dependent Schrodinger equation for this unitary operator u. Okay. So let us understand that at time t equal to infinity, minus infinity, sorry, at time t equal to minus infinity, you had nothing. You had only the bare system, okay. And at time t equal to minus infinity, you have switched on the electric field, okay. So the system, you let the system evolve and come to at the present time or at t equal to 0 and so on. At this time, the many body ground state, let us write this as 0. It is a ground state, but nevertheless it is a many body ground state, which may have interactions inbuilt into it, but of course we do not have any effect of delta H at t equal to minus infinity, and we will call this state as 0 with a ket, understanding that 0 is actually a many body ground state. Okay, fine. So, all right. So, we will do it step by step. So, u of t, it is actually u of t and with a t0 from minus infinity. Okay. So, we set t0 the earliest time, the most primitive time, to be at minus infinity when there was no effect of the perturbation, and after that the perturbation is switched on. Okay. So, the t0 goes to minus infinity, and because now it depends only on one time variable, we simply call it as u of t. Okay. So, you always calculate some expectation value in a perturbation theory by using the different orders of perturbation theory and so on. So, we are going to calculate j of t. And this j of t can be calculated within this 0, that is many body ground state evolves, a j of t and a 0 and a t and so on. So, this you are calculating the expectation value between the known states. So, this 0 is at t equal to minus infinity, but that many body ground state would evolve with time. That is why we have written 0 of t, and we still assume, this is a intrinsic assumption of perturbation theory, that you still have the 0, that is the ground state, to be a valid description of the system. So, your the delta H term has not taken the system too far away from the ground state, so that there is no point in talking about the expectation value with respect to the ground state. But the perturbation theory intrinsically assumes that it still is a you are not too far away from the ground state, and that is why the ground state expectation values can still give you meaningful corrections because of the perturbation to the unperturbed energies or other quantities, like here we are talking about j, average of j. So, what is this? So, this is equal to the 0, and then you have a u inverse. So, I am evolving the state as we have done it here, u of t, now t0 is minus infinity. So, this and then j of t and then u of t and then a 0. Okay. So, this 0 is that many body ground state at t equal to minus infinity. All right. All right. So, we will have this as, so this is 0 and this is a j of t and a plus I over h cross minus infinity to t, and then I use a dummy variable dt prime, and then I have a commutator which is delta h, and so this is at a t prime and then a j of t, and so on. Okay. So, this is the let me use another bracket so that it does not look like the commutator bracket. Okay. Where does this come from? You have to understand that I have done a simplification, or rather skipped one step. Let me show you that step here. So, our u of t is simply equal to, now of course a time ordering is of course required at its minus I h cross minus infinity to t h delta h of t prime and dt prime. Okay. So, this is your that, and then I have to calculate this quantity u inverse t, j t and u. So, u inverse t j of t and u of t. So, this is equal to the time this thing and exponential I over h cross minus infinity to t delta h t prime and dt prime, and now I will write a j of t, and then I will write a exponential minus I by h cross minus infinity to t delta h of t prime and dt prime. Okay. All right. So, now what we do is that we make this expansion, that exponential minus I by h cross, this minus infinity to t and delta h t prime dt prime. I write it as 1 minus I by h cross minus infinity to t delta h t prime dt prime, and then of the order of delta h square is neglected. Okay. So, this term is neglected because the intrinsic assumption of a perturbation theory is that we will not, of course, here we want to see it in the linear response of the system, that is to first power in A, how does the system behave, or how does the properties of the system behave. And also it is true that in keeping with the assumption of perturbation theory, we are not considering any higher order. Okay. So, this thing, let us call it, so this is equation number 3, let us say this is equation number 4, this is equation number 5, this is equation number 6 and this is equation number 7, and so we will have maybe this one as equation number 8. This is equation number 9. So, if you put this in equation 8, putting equation 9 in equation 8, so we have 1 plus, because this u inverse is 1 plus I by h cross minus infinity to t delta h t prime dt prime and a j of t. Okay. J of t is here in equation 8, and then 1 minus I by h cross minus infinity to t delta of h t prime and dt prime. Okay. All right. So, I have two brackets at the two ends, and I have a jt in between. So, I will just do a multiplication. So, this will be simply a j of t, that is 1 jt and 1, and then second term will be I by h cross. I have infinity to minus infinity to t delta h t prime j of t. Okay. And of course, you have to write dt prime there, you can write it, and then the next term will come with a minus sign I by h cross that is 1 jt and the term that is there. You understand that just do this simplification and then you will have so a j of t and a delta h of t prime and a dt prime. You can actually keep the jt outside this thing. Okay, the j of t can be outside and you have a minus infinity to t and so on. Okay, so this is your term and this can be written as j of t, that is the first term, and then I have plus I over h cross. Now you see that this is a delta h j and this is j delta h. So this is like a commutator. So this is written as a minus infinity to t dt prime and this h prime of t, delta h of t, delta h and a j of t. It really does not matter because the integral is over dt prime. So, it is not touching the t, that dependence of j. So, this is the commutator. So, this is the commutator that I have talked about at the end of the last slide here, that commutator. Okay. So, and then there is of course a term which is the j of t, which is here as well. So, and now this j of t is not important for the reason that this j of t is a current density without an external electric field, okay, which can be there due to a variety of reasons, but it is not important for us. We are only interested in this commutator and which arises because of the electric field. All right. So, we got an expression for that for your j. Now, let me get an expression for just a component of j, that is maybe jx or jy or jz and so on and so forth. So, this is equal to 1 by h cross omega, and now I put the explicit form. I use your delta h equal to minus j dot a, and a I use it as what has been written earlier, that use a as e over I omega exponential minus I omega t. Okay. Okay. All right. So, if you do that, then the particular component of the current that looks like this, and this is equal to 1 over h cross omega, and then minus infinity to t and dt prime and a 0 and a j I t prime and a j I t and a 0, and you have to write the electric field. So, this is E j exponential minus I omega t prime. Okay. So, the commutator of delta h and its t prime and j at t takes this form, because delta h is nothing but j dot a, and then you use the relation for a which we have assumed within a certain gauge, and so this is equal to a j I t prime and a j I t. So, this we taken within the many body ground states and so on. Okay. Now, it is easy to see that, or rather it does not harm us if we assume the system is time translationally invariant. That is, we can translate time without any sort of breaking any symmetry. So, it has time translation symmetry, because there is nothing that breaks that time translation symmetry. So, what it means is that there are two times t and t prime that you see there. So, these two times can be converted into one time if there is a time translational symmetry, which means a t minus t prime can be written as some t double prime. This is perfectly fine, and we can in that case the limit actually changes from minus infinity to t. So this becomes minus infinity to t. This limit becomes equal to 0 to infinity. Okay, you can trivially see that j I t in that case becomes equal to 1 over h cross omega, and from 0 to infinity, and we have a dt double prime, and this is equal to 0, and j I 0. So t prime we are setting to 0, and then we are replacing t by t double prime because of the translational invariance, and this j I t double prime and 0 here, and then we will have an exponential. So there is an exponential I omega t there inside. So this is multiplied by e j exponential minus I omega t. Okay. So this is a commutator. We should not forget that this is a commutator. Okay. So j I at 0 and j I at some t double prime, and then you have this thing to be present there. So the only time dependence is coming as a harmonic function exponential I omega t and so on. So this gives you the linear response of the conductivity. So the conductivity is proportional to, so remember that relation Ohm's law, that J equal to sigma E. Now you have calculated J, which is the expectation value of J, and this is equal to the sigma is here, and this will be an exponential minus I omega t here. So the sigma xy, which is the Hall conductivity, or the Kubo formula for the Hall conductivity, is sigma xy equal to 1 over h cross omega 0 to infinity, and you have a 0 jy 0 jx t, a commutator 0, and exponential I omega t, and so on. Okay. So that is the formula for the Hall conductivity, and this is a well known result. So this is the result for the Hall conductivity, and which involves only commutators which are jy, that is the current density in the y direction, and the current density in the x direction at a different time. One of the times has been set equal to 0, and this sigma xy is a dynamical conductivity because it depends upon the frequency. And of course, when we take the DC limit, that is, we will put omega equal to 0, this will become the Hall conductivity that we have seen. Okay, this is Kubo formula for Hall conductivity. And if you want the longitudinal conductivity, that also can be done. So you have to have sigma xx, where it will be the current operators at two different times, but in the same direction. So that will give you the longitudinal conductivity. So what we do next is that this is pretty much the formula that we wanted to derive, but this is not yet in a form that we can use it to compute. Okay, and let us get it into a form that's we can compute this. And so what we do is we can write down this j of t to be equal to some u inverse j of 0 and u, and we have seen this. This is the interaction picture. This is how the operators transform, and u is nothing but exponential minus I h naught t by h cross. Okay, then we can use basically the eigenstates of h0, which we know. H0, which are say m, n, and so on and so forth. Okay. So then we can write down the sigma xy omega by introducing these states, the basis states of, or the eigenstates of H0, as 1 over h cross omega 0 to infinity and a dt exponential I omega t and I use the completeness of states, that is use this n that's equal to 1, the sum over n. So this is there, and then you have a term which is 0 jy n jx 0 and a minus 0 jx n jy 0. So this is the simpler form, in the sense that I have used the information that is already inbuilt into the problem. That is, we know these eigenstates. Okay. So in a given problem, these states will have to be known, these n and 0 and m, etc., all these things have to be known. Okay. And of course, we have to write down the energy exponents. So this is equal to En minus E0 t over h cross, which is that exponential I omega t, and this is also exponential E0 minus En t over h cross. Okay. Now, offhand it looks like you are calculating the velocity operator, because J is nothing but if you write it's NeV, even if you don't write that n, which is an electronic density, it's still E into V. So V is the velocity. So it's a y component of the velocity between these states of h0, which are known, and then x component of velocity, and then multiplied by an exponent involving the energies of those states, and minus of the jx and the jy. They are in opposite order, or just the reverse order, because we are talking about a commutator here. Okay. Now we'll perform this energy integral. That is and in order to perform the energy integral, there are two things that you need to keep in mind. Okay. Now the energy integral looks like dt exponential I En minus E0 plus omega into t, and the other one looks like so 0 to infinity, both the cases, and dt exponential I E0 minus En plus omega t. I mean t, and then of course there is a h that one needs to put there. Omega by h cross is energy, omega equal to h cross omega. Okay. So you have these integrals that you have to perform, and these integrals will diverge at infinity because these are exponential integrals. So the standard technique for calculating these integrals such that they don't diverge is by introducing a little bit of damping. Okay. So let's say that these are En minus E0 whenever you have these, if you just perform the bare integral, it will go to infinity. And what you do is that you change omega to omega plus some I eta or something. Okay. So once you do that, this will not diverge farther because of this small eta, and it will go into the complex plane. And there is also a reason that you put a plus and not a minus, because you are considering t greater than 0, right, from 0 to infinity. So there is no negative time. So you want to do a contour integral by enclosing it in the upper half plane, so that you can use Jordan's lemma. So this integral over the real line is converted into a complex integral by sort of trying to close it from the upper half, such that in this big circle, so this is from 0 to infinity. So you close it and it becomes a closed integral, and then you can use the residue theorem. Please get used to this complex integrals, because they are they're ubiquitous in terms of all these contexts of condensed matter physics, Green's functions, and so on. Okay. So once you do that, then the sigma xy takes a form which is equal to minus I over omega. So after you do the integral over time from 0 to infinity by using the complex integral. Now just to remind you, so you initially had only over the real line from 0 to infinity. What you do is that you introduce small imaginary parts so that the pole, that is where wherever you have pole of this, or rather this the resonance, you bump it up by a plus I eta here and enclose it. Now it encloses this simple pole or whatever is the nature of the pole, and then you can use 2 pi I into sum of residues. Sum of residues. Okay. And then you perform this integral. Please go through this text called, there is a textbook on complex analysis by Churchill. Okay. It is a very good book for complex analysis, which tells you how to do the complex integrals and so on. So this is equal to that, and then of course your n, which is this n here, this is not same as 0. So these are some excited states of the system, and that makes sense because for carrying the current it has to visit the excited state because there is a conductivity in the system. So the system would go from the ground state to the excited state, and the excited states are assumed to be different than the ground state. So this is equal to 0 j y n and n j x and 0 divided by the energy denominator, which is given by E n minus E 0 and a plus another term. So the term is 0 j x n n j x 0 divided by h cross omega plus E 0 minus E n. Okay. So you get this energy denominator. Now we are almost there, excepting that we have to take the DC limit, and DC limit means omega going to 0. And how do we take that? Let us sort of write down the denominator as E n minus E 0. Okay. And this is equal to you write it as E n minus E 0, and you write it as 1 plus h cross omega divided by E n minus E 0, and then you write it as 1 divided by E n minus E 0 multiplied by 1 plus h cross omega divided by E n minus E 0 to the power minus 1, and they do a binomial expansion and keep only the term which is with the first term only, which is linear in omega. So this is 1 by E n minus E 0 plus, so this is equal to minus h cross omega divided by E n minus E 0 whole square. So I do a binomial expansion and the minus sign gets replaced here, okay, at this place. And then you do this, and then of course these are terms which are omega squared that are neglected. Similarly, you do that for the other term, the second term inside the square bracket, which is h cross omega plus E 0 minus E n, and this will be like E 0 minus E n and a minus h cross omega divided by E 0 minus E n whole square and plus omega square, order of omega square, which again can be neglected. Now we actually drop this term, the first term which is here. So these terms we drop, okay. In fact, for Hall effect these terms do not make a contribution, and you keep the term that is linear in omega, because this has no omega part. So, this is like a DC thing, and I mean DC contribution, which is not an important thing, and in any case that they really do not in a translationally invariant system, they do not contribute to the Hall resistivity and so on. Okay. So, what you do is you put them there in that equation, and then you see very nicely there is a omega in the denominator of equation. So, I have equation 9 and let us call it as equation 10 and equation 11, which is the Kubo formula, and say this is equation 12, again another form of Kubo formula, 13, which is another form of Kubo formula. We are progressively getting better and better in terms of its computability. Okay. So, now if you keep this term, either of the term which are same, because there is a h cross omega and there is a square in the denominator, and the square means that En minus E0 square is same as E0 minus En square, and the omega will cancel with the omega in the denominator of equation 13. Okay. So, once you do this, your sigma xy becomes equal to now I do not need actually the omega gets cancelled. So, it becomes a DC expression, and this is equal to I h cross again n not equal to 0 and 0 j y n n j x 0 and minus 0 j x n n j y 0 j y 0, and either you call it E n minus E 0 whole square or E 0 minus E n, which are same. Okay. So, this is really the Kubo formula for the Hall conductivity. Okay. You can also get the longitudinal conductivity. There are many things that we have said which are important, that the diamagnetic term should also come in order to calculate the conductivity, the longitudinal conductivity. But here nevertheless we are interested in the off diagonal form of conductivity, which has this form. Let us call this as equation 14, and this is what we wanted to calculate. And this, when you calculate it on a quantum Hall system, it gives you values which are h over e square, and there is a integer in the denominator, or you can call so the conductivity. So, that is the resistivity. The conductivity is actually n into e square over h, where n is an integer. Okay. That is where we stop for now, and we will continue from here.